So today we will learn about K-connected orientation. More accurately, KH connected. So for the graph and diagram, we define the connectivity. There is one thing different, is that for graph case, undirected graph case, the K connectivity means that once we delete a vertex set W of at most K-1 vertices, in the remaining graph, we should still be able to find the path between two vertices. However, for the directed graph case, what we want is, even if we delete at most K-1 vertices, we should be able to find the path from U to V, and as well as from U to, V to U. And this, because of that, sometimes, the connectivity for this diagram is denoted as a strong connectivity. So we say a diagram is strongly connected if from U to V, for any vertex U and any vertex V, you should be able to find the path, then this is strongly connected. And then it's K connected or strongly K connected, if same is true after deleting K-1 vertices. And for edges, you also, define it similarly. Instead of, deleting vertices, you can consider the situation of deleting edges. Then that defines, the connectivity. Then it's natural to ask how these two are somehow related when we orient the edges of the undirected graph. So directed graph here, or more specifically oriented graphs, are obtained from graphs by orienting edges. Once you have an edge, you can either orient it one way or the other way, and that gives you an oriented graph. As both of the connectivity measures how well connected, how well connected those graphs are in a slightly different sense. So one can ask that whether, if we are given a highly connected graph, can we orient the edges so that the resulting graph is also somehow highly connected? And it's more, natural to consider the edge connectivity, because we are orienting edges, so intuitively it might be more, related to edge connectivity than connectivity. In particular, in the undergraduate graph theory, we learned this Robin theorem. We learned that a graph G has a strong orientation, which means that you can orient the edges so that the resulting oriented graph is strongly connected, if and only if G is two-edge connected. And we proved this by using ER decomposition. So G is two-edge connected, so it means it has weak ER decomposition. And by using that, we proved in the undergraduate graph theory. So what we want to do is we want to generalize this to higher connectivity. So what we want to prove is the Nash-Williams orientation theorem. Saying that, let's consider a multigraph. A multigraph has a KH connected orientation if and only if it is 2KH connected. So here, strongly connected is same as strongly edge connected. So this is actually edge connectivity 1. So both of the, theorem says that once you orient the edges, you might lose the connectivity by a factor of 2. So 2KH connectivity become KH connectivity, but you can make sure that you don't lose much more. it's kind of easy to see that this is best possible, because if graph is 2H connected, then there could be a vertex with 2k, degree 2k. In that case, no matter how you orient it, either there are at most k edges going inside, going into V, or at most k edges going out of V. So which implies that its connectivity as an oriented graph must be at most k. And this is something that we want to prove today. And actually, Nash-Williams' theorem is stronger than this. And he defined that on orientation, of a graph, say orientation T of a graph G is well balanced if the number of, the edge connectivity between X and Y, the number of edges to delete to make sure that there is no path from X to Y is at least kappa prime G of XY over 2. So this is local connectivity, local edge connectivity. So you can not only, keep the global connectivity as a half, but you can, do the orientation so that all the local connectivity is, not lower than the half of it. And strong orientation theorem says that Nash-Williams' strong orientation theorem says that every, graph G has a well-balanced orientation, which trivially implies this orientation theorem. Anyway, today what we will prove is this orientation theorem of Nash-Williams. In this subsection, let's write this delta of X for vertex at X over graph to be the number of edges leaving X in a graph or digraph. So for graph case, we just count the number of edges whose one end is in X and the other end is outside of X. So we don't count these edges or these edges. For digraph, we only count the ones that's leaving. So these blue ones are not counted, while the black edges are counted. So how do we want to prove this? So we want to prove it using induction. Induction on, say, number of, vertex. And idea is that if you have, say K is 2, so 4H connected graph. If there are vertex with degree 4, then what we want to do is, let's say this is U1, U2, W1, W2. Somehow we want to transform this to graph which look this way. So we get rid of V, and then we add edges, add a matching inside the neighborhood of V, and make sure that this is K edge connected. So 2K edge connected, 2K edge connected. And then in here we apply induction to get an say orientation, and then orientation of the graph, and then we use that orientation in the original graph in such a way that this orientation give us this, and this second orientation give us this, and then make sure that this is again K connected. So that's our plan. That's what we want to do. And for that, we need to make sure that somehow we can pair this up, U1, W1, U2, W2, so that this resulting graph is 2K edge connected. So we want to pair this up in some way. And moreover, we want to pair them up one by one. While doing, one of the downside of pairing it one by one is that if we pair this up first, U2, W2, U1, W1, and we want, the best situation is you do it once and then you show that this is 2K edge connected, and then you do it again and you get this, and this is 2K edge connected. If that's possible, that would be the best scenario. Because that would be already sufficient for our purpose. But simply that cannot be true, because in here, this V has degree only 2, which is strictly smaller than 2K. So this cannot be 2 edge connected. So what we do is we make some new notion which is slightly weaker than edge connectivity, but all this graph and this intermediate graph also satisfy that notion. So what K connected means? So let's say T connected, TH connected. It's easy to check that the TH connected means that for any vertex at X, the number of edges living there is at least T for all, say, non-empty proper subset X of the vertices. So as long as X is not everything and not empty set, the number of edges leaving X is at least T. So this is equivalent. But for this graph, this is no longer satisfied for this V. Delta of this V is only 2 here, which is smaller than 2K. So, but you can observe that for any other set but this or trivially its complement, any other set except these two, this condition is still satisfied. So that motivates us to define the following weaker concept of connectivity. So a multigraph G is a TH connected. Relative to a vertex G. So TH connected relative to certain vertex. If the number of edges leaving a set X is at least T, whenever X is a proper non-empty subset, of VG other than G or the complement of this one vertex. And then let's give some name of this operation. Operation of, changing this graph into this graph. If G has edges UZ and GB, then the UV shortcut of G is the graph G minus UG minus GB plus UV. So now what do we have to prove? In this plan, we have to now prove that once you have this 2kh connected graph, and then you apply this shortcut operation for some good u and v, so that the resulting graph is again 2kh connected. So this is something called shortcut lemma. Robust. So if G is a vertex of, say, even degree in a multigraph, G that is TH connected, relative to, say, G, then for all vertex U in the neighborhood of G, there exists V also in the neighborhood of G, such that the UV shortcut of G is also TH connected relative to G. So this is exactly, what we want. We have this graph, and then you take the shortcut, then that's again 2kh connected relative to this vertex. And then you do it again, then this is again 2kh connected relative to this vertex. But this vertex itself is isolated vertex, so if you just forget it, then the resulting graph is 2kh connected. So we later apply induction hypothesis to here to get the orientation, which automatically, naturally give a orientation on the original graph, which is our desired one. That's what we want to check later. So note that this is true for any t, but we only prove for even t, because that's, enough for our purpose. And also the proof for even t is simpler. So we want to prove this in the next video.